Good morning or good afternoon, everyone. Once again, this is Mr. Steele. This is actually the final lecture during the time at which I'm supposed to be gone with this back surgery, which actually honestly can't come fast enough today. I've reached down to put on a shoe and I'm struggling right now, but I'm going to try to finish this last lecture to make sure that they're all done, and then hopefully I'll feel better along the process of doing this. More relevant to you is today's final lecture, which I've promised for the last couple days we'll go through and actually add a more realistic application to the implicit differentiation work we've been doing the last few days. As I said, the title of this topic is called Related Rates because our goal is going to be to use implicit differentiation to relate multiple different changing quantities together and to use that relationship in order to solve for one or the other. So again, we're going to be literally relating rates together using implicit differentiation. Now, before we jump in and start to look at what this looks like, and I go through a number of examples, enough examples, in fact, that I might even warn you that this lecture oftentimes takes more than one day. It just kind of takes a while to go through all the examples and do a couple try-its and everything in there too. What I want to point out is that what we're doing here is slightly different than what we did before. And to kind of help with that, and to help make that clear, what I've started with first is I've written out the same problem twice, and I've listed it, one is old and one is new. Specifically, what I mean by old is the traditional implicit differentiation. So when we did implicit differentiation in the past, and by past I mean like the last 2 days in all likelihood, our goal was to figure out what dy dx was equal to, which we often referred to as y prime. That meant when we differentiated, as we've done a few times here, we took the derivative with respect to x of the entire piece, and we were differentiating with respect to x on the x squared, as well as that y squared, as well as on the right side, which is 25. Now when we went to do this, the derivative with respect to x of something involving an x was really easy to work with. That just gave us our traditional derivative, which in this case was 2x. Same thing with the constant. Of course that derivative is 0. It doesn't matter what we're changing with respect to. It's flat. Its slope is 0. Our difference was when we got to the y functions, we imagined for a second that this was instead something explicitly connected to x, like y equals f of x squared, and then we used the chain rule. And the chain rule was able to discover, or what the chain rule did, was it gave us the derivative we'd expect, which is that if x squared's derivative is 2x, y squared's derivative is 2y. But because of that implied connection between x and y, we multiplied by dy dx, or as we did for simplicity, y prime. This relationship then gave us a pathway to solve for y prime and give us the dy dx slope expression we were looking for. Now that process is the same one we're going to follow here, but there's going to be a big change. And the biggest change comes actually at the very beginning of this work that we've been doing. Specifically, instead of differentiating with respect to x in these related rate problems, we're going to be differentiating with respect to a third variable that will now become independent of the other two. That variable is t. And specifically, we choose t in almost every case because of the fact that way we can relate everything to time. And so in a sense, what happens here is we end up trying to determine the rates at which x and y are changing relative to time. So they're each changing independently now. Y isn't dependent on x in the same way it was before, at least not in that same way it was in the past. So in this case, it's still an implicit differentiation, but in this case, when we differentiate with respect to t, then our goal is a little bit different. We can't seek just one single variable in the traditional sense because there's going to be multiple things changing. So in a sense, what you can imagine is when we're working through this, we would be differentiating each term of this expression with respect to t. So we'd have ddt of x squared, ddt of y squared, and ddt of 25. Now some of these are easier than others. The right side is clearly equal to 0, but on the left side, now we have two situations where we have a variable related or being differentiated with respect to another one. So in a sense, that means that both of these things, both x and y, each have to get treated as special in the way implicit differentiation treated y. Because in a sense, each one is now changing with respect to time. So for the first one, our derivative would be 2x, but then we'd multiply by dx dt. Because of course, the rate at which x is changing with respect to time is relevant here too. Likewise for y, the derivative of y squared would be 2y, but now we'd have to multiply by dy dt to satisfy the chain rule. And in a sense, what we've just created is we've created for ourselves a relationship that connects the rate at which x is changing to the rate at which y is changing. And since it's all in one big equation, we would then be in position to figure out what the connection is. If we knew one rate value, like for instance if I told you what dy dt was, and we knew the ordered pair we were looking at, we could very quickly solve for dx dt. Same thing if we knew some sort of connection between x and y and dy dt. Basically, this would open up everything else for what we were going to look at. Now, before we go forward and look at our first kind of like basic example, and then eventually jump into some more involved ones, let me point out that a good way to look at this is to think about the fact that both x and y change over time. So think about that for a second. If x and y are both changing over time, another way to phrase that would be to say that x and y are both dependent on the time t, which means you could really look at x as equal to x of t, in other words, x is a function of time, and you could similarly say that y is equal to y of t, so that there's some connection in there. Given that, we could rewrite our entire equation here as x of t squared plus y of t squared equals 25. And then when we're looking at these derivatives, I think you can more clearly see the chain rule popping its head in. In a sense, what we're doing in here is we're taking each term's derivative separately, each one as a function of time. So for instance, on the first one, we'd have 2x of t, because of course that would be if you let u equal x of t and the outside be u squared. And then of course we multiply by the derivative of the inside, which is x prime of t. Again, making clear what I'm talking about here one more time. If we let the outside be u squared and the inside be x of t, we'd end up with our derivative via the chain rule exactly like we see right here, which is just another notation for the same thing up there, just kind of written differently. So keep in mind as we go forward, that's really the implication here. We're going to be assuming these variables are changing with respect to time now, and that means that we need to treat them all kind of differently. Now, of course, if one of those variables wasn't changing, we could treat it as a constant, but of course that's going to have to be provided for us in a problem. So for the moment, just know that this is kind of like, I'm trying to think of a good word for it. It's like super implicit differentiation. It's like everybody's special. I think in past years I've talked about it as like the communism of implicit differentiation. Rather than treating the elite class of aristocrats known as Y as special, in this case everyone gets to be there. Like everyone gets that special treatment, which I'm not sure if that's exactly how communism works out, but you know, here we are. So with that in mind, let's look at our first like very basic like kind of pared down problem. They'll let you really focus on what's happening mechanically. So our first question here is going to ask us to differentiate with respect to t. So it's very explicit about what our task is. We want to take the derivative with respect to t, which for our purpose means that we want to do d dt of the equation. I'm pretty sure at some point I'll make a gag about DDT being, I believe, a pesticide, so if that pops up, you'll know it's where it's coming from. So in looking here, we want to DDT this equation, in other words, differentiate it with respect to time. So as we go through here, our first move is to look at what that would actually turn out to be. Now again, we're used to thinking of this as some sort of explicitly defined function, because y equals something of as a function of x. But unfortunately, because we're differentiating with respect to this third variable t, representing time, we don't have that same luxury of being able to just spit out y prime equals something. So in this case, what this looks like will be, of course, doing this mechanically slowly first. We'll speed this up in a little bit. We'll have ddt of y on the left. On the right, we'll have ddt of 5x squared plus ddt of 3x plus ddt of 1. So there's kind of the mechanics of it, using only the sum and difference property of differentiation. Now in looking at each of these pieces, you can kind of imagine again if you want to, this is y of t, this is x of t, this is x of t, and you can do it that way. Or we can just treat it as everybody gets implicit differentiation chain rule work. So specifically here, ddt of y is going to be dy dt, but more realistically I would probably just call that y prime. Likewise, for the next one, 5x squared, the derivative is going to be 10x, but then we'd still have the derivative of the inside, which would be formally written as dx dt, or we could write it as 10x times x prime, because of the fact that x is also changing with respect to time. Similarly, ddt of 3x is 3 times the derivative of x with respect to t, otherwise known as plus 3x prime. And then the last one is, of course, 0, because, yeah, 1 is not changing very much. So from there, we now have our relationship. So writing this out a little bit more cleanly, we would get that y prime is equal to 10x plus 3 times x prime. And then what we'd have just done is we'd have now connected the rates of change for y and x, and they would have a single relationship. Now this problem kind of sputters out because it just kind of ends there. We didn't have any real purpose for working through this except to get you comfortable with the mechanic of differentiating with respect to time. But in truth, from here, we would have to move forward. Like say we were given a point 3, 9 3, at x equals 3, for instance, and we were told that y was changing at a certain rate. We could then use that information to solve for x prime and figure out what rate x was changing at. So we'd be able to leverage this relation. And of course it's a relation because there's an equal sign in there. And it's a relation of two rates. And those rates are y prime and x prime. So once again, there's your name for the topic today. We're talking about related rates because we're literally relating rates together, and then we're leveraging the information we have to solve those for one or the other. So there is kind of, as I said, a very boring mechanical version of what related rates, or how to attempt and use the differentiation with respect to t. But of course, that's not going to be the typical problem we're going to work on. We're instead going to give you some application questions that let you connect some geometry and physical spaces and see how changing things in changing one element or one dimension actually affects other ones. And I know I just made that sound a lot harder than it needed to, but at the same time, I want you prepared to know that there's going to be some geometry in here. There's going to be some interesting work to be done. So let's take a look at our first full example, which should be on the list of problems, the massive list of problems that's provided for you. Okay, so our first question here, the first example that we are going to hit, is what I hope is the first one on your page. Again, I don't have that page in front of me, so I'm just going to have to make sure it's there when I prepare materials for you. So in here, we are told in this question that a square is being enlarged electronically on a computer such that its side length is increasing at 24 pixels per second. At what rate is the square's area increasing when its sides are 10 pixels long? Now this is a little bit weird to start with, but I'm starting with a very simple problem because it's one that I can actually demonstrate for you. So I'm going to actually see if I can cheat this process a little bit. No, I don't want to make it bigger. There we go. So here's our scenario. A square is being enlarged on a computer. So I want to insert in here a shape, and I'm going to insert in a square. So here is a square. To make it a little easier for us to see, I'm going to get rid of the filling and then make the outside much bigger. So there is our square. One thing I want to do is I want to lock the dimensions a little bit here. Do I have size? Really? Okay, there we go, size. I just want to lock the aspect ratio so that way it doesn't change from being a square. So with this in mind, it says this square is being enlarged on a computer such that its side length is increasing. So this, for instance, could be what that looks like. The side lengths are increasing. Oh, that got a lot bigger. So there we go. So our square's side lengths are increasing. It says at 24 pixels per second. I'm not sure I'm that good at estimating, but it should be somewhere in there. And it then asks us at what rate is the square's area increasing when the sides are 10 pixels long. So for instance, what you have to imagine are kind of two things here as we go into this first problem. And again, I'll do the mechanics of it. I'm just trying to set up like what's actually happening first. So we start with a little square, and that square is getting bigger. We can tell that it just keeps getting bigger according to what the problem told us. What we're interested in, though, setting aside the scale of this, is we're interested in how fast the square is changing at a given moment. So it's like the square was growing for a while, or being enlarged, and then someone took a snapshot right here. And of course we knew the square kept growing, but someone took a snapshot of the square right here, and they wanted to know how fast was its area changing at that moment. Obviously there's lots of change happening here, but at a given moment, the amount of change might be different, particularly in this relationship that has something to do with quadratics. So that's kind of the nature of every related rates problem. You can imagine you've got a situation where, for instance, someone is running, and then someone takes a snapshot of the runner in motion. And although in motion, or even though in that moment the motion doesn't look like it's happening because it's in a still photograph, the idea is they were moving at a certain speed, and we're interested in that speed at that snapshot moment. So I'm hoping that added a little bit of context here, but I know that it might not have, so let's go in and actually work through a problem and show you what this looks like. It's not that bad, but there is some involved work to be done here. So first of all, the first step I want us to tackle is to make sure that this is as concrete as possible. So the first move I'm going to make in a related rates problem, whenever possible, is to draw a diagram. I want to diagram the situation so that I have something to label, something to look at, something to imagine changing. So in this case, we have a square. And the nice thing about a square is they're easy to draw. So, of course, easy to draw is easy for me to say when I'm not very good at drawing straight lines. So let me cheat a little bit here. Again, all I'm trying to do is draw a square. And then finally, let's go. Yep, not my finest work here. Someone's probably sitting out there going, why didn't you just copy the square from Microsoft Word? This isn't what I want to be doing when I'm hurting like this. There we go. There's our square. If you don't think it's a square, you're just going to have to take it and enjoy this. So there's our square. I'm going to actually make it a little bit bigger. I can't make it bigger because I underlined the word square. There's our square a little bit bigger, and of course we said this was a square. That illustrated for us what we were drawing. Okay, so there's our square. We drew a quick diagram. In this case, because we were talking about a simple geometric shape, that diagram wasn't very difficult to draw. Other times it might be more difficult to render, so just keep that in mind. Now our second move is going to be to write an equation. And when I say write an equation, I don't just mean 4x equals 10. I mean that I want us to somehow start to figure out how to relate the things that we're interested in this problem. So specifically, we're talking about a square. Like in a sense, I'm just going to put a little star here. We're talking about a square. We're talking about its side length changing. And we're also talking about the rate at which the square's area is changing. So in other words, what we're seeking right here is we're seeking some sort of relationship, some equation, that contains information about a square's area, related to its side length. Well, I don't think that's going to be too hard. The area of a square is equal to its side length squared. Right? That's just length times length. In fact, I'm not going to use S because it looks too much like a 5. I'm instead going to use L. The area of a square is length squared. So, of course, this is L and this is L. And I bring this up as our first starting part. Shouldn't have drawn that picture on there. I bring this up as our starting part because this, in a sense, gives us the key. This is going to be how we relate those rates together. We start with the geometric relationship, or just the algebraic relationship that we have, and then eventually we're going to differentiate it with respect to time. So we're starting there. From here, the next move is, you saw me get ahead of myself a little bit a second ago, but our next move is going to be to try to connect that to our diagram. So basically we're going to connect via labeling. So we're going to label our diagram. Now when we do this, we want to label all relevant dimensions, but as we do it, make sure that you have a variable anywhere where something is changing. 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 So in our case, we want to label the diagram anywhere where things are changing. Well, I already did it a second ago, so spoiled the surprise. But in our case with our square, of course the area is changing, but we can't quite label that the same way as labeling the side lengths. And because this is a square, the side lengths have to both be the same, so of course those side lengths are changing together. They have the same rate of change, they're the same length. So there our diagram is labeled, which is just kind of nice to see. And you'll notice that I'm marking out here L on the outside. This is my own personal convention, but I like to label the changing stuff on the outside of the diagram. And the reason for that is that there's more information provided in here. But I don't need to worry about that just yet. Instead, I wanted to focus on what was changing. I've got that all in place. And now it's time for the one little bit of calculus that we're really doing here. In step 4, we are going to differentiate. Of course, I got to write out that whole word. We're going to differentiate with respect to time. So in here, what's pretty simple. We've got our relationship, a equals L squared. That connects the area of a square to its side length. We want to differentiate it with respect to time. So we're just going to ddt the equation. Now when we do, again, being super formal, if I were to be super formal, I would probably write the dt is equal to the derivative of the next part, I'm not going to do that. I just want to be as realistic as possible. So the derivative with respect to time is going to be a prime, and that's going to equal 2L times L prime. Again, what I was trying to avoid is writing out the dA dt equals 2L dL dt, which is nice and precise, but again, I prefer the primes myself. So there is, like in a sense, like this might not seem monumental to you, but there is our relation between two rates. We have already related rates together, so that's a really huge moment. And as I said earlier, that's really the only calculus we had to do in this problem. We have a relationship between all those rates. Now it's our job to start connecting all these rates together and finding the missing pieces. So from here, we're going to plug in the given information. And as a part of this, I'm also going to use my diagram. So specifically in here, it tells us a lot of information, but specifically it asks at what rate is the square's area increasing when its sides are 10 pixels long. So in a sense, this is telling a specific value of L. This is the snapshot moment. It says that we were interested in observing when the square was increasing its size, but we want to know specifically how fast it was changing when the side lengths were 10 pixels long. So what that means is we're interested in the snapshot moment in here. So what I do is I label on the inside whatever it is that represents the moment in time, the specific length at that instant that we were interested in looking. With that said, that also means that in our equation, we can evaluate this equation when L equals 10. In addition, there's one more piece of information provided up there. It says that the length is increasing at 24 pixels per second. What that tells me is that we know the rate of change. We know L prime is equal to 24 as well. So as L is getting bigger and bigger, it's growing at the rate 24 pixels per second. And with that in place, we can actually plug into our equation. We'll have A prime equals 2 times L, which we said was 10 pixels, times L prime, which we said was 24 pixels per second. And this, you'll notice, is now a complete equation. All that's left would seemingly would be to evaluate it and figure out what A prime is equal to. So A prime in this case is 20 times 24, which is 480. And so there is our numerical answer. The area is changing at 480 somethings. So again, all we had to do is draw that information out of the problem, and you can see up here I'm using color to make it really clear where I'm drawing that information out of. Because yes, I'll admit that reading is a huge part of these problems. I can't lie about that. To wrap this up though, our final move is of course to acknowledge the fact that this number 480 doesn't really provide us enough context. We want to know specifically at what rate is the square's area increasing. Is it in inches per minute? Is it in miles per hour? Is it in kilometers per nanosecond? Like, we want to be able to figure out what units we're measuring in. So the final step of this process is to determine units. So in here, there's a couple different ways to do this. My personal way is very, appropriate in the sense that it's kind of implicit. I read through the problem and I try to anticipate what the units are. I'm going to show you that first and kind of talk you through my reasoning. After that, I'll show you how you could formally find it if you weren't sure. So in here specifically, we're talking about an area. I know that areas imply units squared. So my thought is we're going to have units squared per time unit, because that way we'd also have a rate of change. In fact, if you wanted to, if you rewrote this as dA dt equals 480 something, you might be able to see how those units come up too. We need units of area over units of time. Well, in our case, we were measuring lengths in pixels, so area units would be in pixels squared. And then time units everywhere in here were measured in seconds. So we'd go pixels squared per second. And in fact, that is the answer that we were looking for. The area is changing at 480 pixels squared per second as we work our way through. Now, if you weren't comfortable with that, if you prefer something else, your alternative would be to go back up to your step right here and to focus your attention on what the units were within there. So A prime is equal to 2 times L. Well, L, it was mentioned as 10 pixels. So you can imagine putting 10 pixels in there. And then the units of change for L were pixels per second, which meant that this was then being multiplied by 24 pixels per second. I should do this correctly. Sorry, I'm trying to be as accurate as possible. So with that in place, we can see that our units, like in addition to getting out our answer of 480, we can see that our units would be pixels times pixels per second, which of course becomes pixels squared per second. So there is a second way to get there if you're not 100% sure. Of course, it may not be my personal preference just because I don't like cluttering up the equation, but if it's something that you have trouble finding, there's a good way to get in there. And I will say, typically I'll include the words include units in here. I think I just haven't updated those phrases at all here so far. Now with that said though, let me point out that it might be time to celebrate a little bit. We've actually just solved our first official related rates problem. We did that by drawing a quick little diagram. It wasn't super essential here, but it's nice to have that context of a picture. We then wrote an equation that connected all the elements that were changing in here. In our case, in this problem, it was the area of a square based on its side lengths. Then we labeled our diagram to get some context here. Not as essential as it will be later, but still good. Then we differentiated both sides with respect to t to find those rates that we wanted to relate together. Finally, we plugged in all the information from the problem, which required a little bit of reading, might sometimes even require a little bit of algebra or mathematics. And then finally, we determined the units through one of two methods, either inspection or actually plugging in units and carrying through the operations. So with that said, there is your first related rates problem, but don't you worry, there's many more to come next. Moving forward, I want to look at some other problems that might kind of pop up and start to get you comfortable. I'm going to do one more kind of traditional related rates problem, and then after that I'm going to let you try one on your own, so it should work. So our next example. While preparing for a party celebrating the end of homecoming, Jesse had to blow up a spherical balloon. So spherical, of course, means that it's in the shape of a sphere, so it's perfectly round. Every cross-section is a circle. So if she blew air into it at a constant rate of 10 centimeters cubed per second, what was the rate of change of the radius of the balloon when the radius was 3 centimeters? So in this case, again, it's not going to be a perfect picture here, but if you want to kind of visualize what's happening here, we've got someone blowing up a balloon, and of course what's happening is as the balloon gets more air punched into it, there becomes a larger and larger radius for the balloon. Our question is, at the instant when that radius is, say, 3 centimeters, what was the rate of change, or excuse me, what was the rate of change of the radius at that moment? So again, we've got a sphere getting bigger and bigger. Actually, I drew a circle, but same idea. So there's our scenario. So in our case here, I want to try to draw a picture. So I want to start with a diagram here. It's not going to be super essential, but I think it's, again, always nice to have a little bit of context, to give yourself a moment to make sure you can interpret. So first and foremost, there is a sphere. Adding that little bit of perspective. Yes, I am an artist. So our radius for the sphere is right here. I'm going to call that radius R. And then from there, the other thing was it says that a person, Jesse, is blowing up the balloon. So for the sake of simplicity, let's see if we can draw something accurate here. Whew. I'm not sure that my drawing is super accurate here or valuable. If you know Jessie, please don't mention this drawing to her because it's embarrassing to me and all of humanity. So in any event, though, we'll just kind of pretend that's the person blowing up the balloon. And it's spherical, at least we got that. So we started with our diagram, had a little bit maybe more fun with it than I intended. Our next move is going to be to write the equation. So in this case, the equation was provided for us. And you should expect any advanced, like 3D geometry equations to be provided for you almost every time. So in this case, they're telling us that the volume of a sphere is given by 4/3 pi r cubed. There's the garbage truck going by. So there's our equation. In this case, it was given to us, so that was really nice. Our next move is to label the diagram, but you can see I'm kind of doing that implicitly with my diagram anyway. I'm going to say that that's r, like that's our radius changing, and then specifically we are interested in the rates of things when r inside is specifically 3 centimeters. So that's our snapshot moment that we're looking at. From here, our next move is to actually do the calculus. We've got the relationship. We've got a picture to support us. We're next going to differentiate with respect to time. So again, the implication here is that both v and r are changing as a function of time. So some might even ask you to think about this as v of t equals 4/3 pi r of t cubed. Like, that's another way to look at it, using the kind of notation that's here. So you might put that in your head as well. That's kind of our starting spot. I'm not going to draw another head. That hasn't gone well for me today. But from here, we can differentiate with respect to time. We're going to get dv dt, which we can call v prime. We're going to then have 4/3 pi times the derivative of r cubed, which is 3r squared, times r prime, or dr dt. So pulling some stuff together here just for the sake of cleanliness, I see the 3's are going to divide away. We're going to get 4 pi r squared, which might be interesting to you if you happen to know the surface area formula for a sphere, but for the moment we'll just keep moving forward without that. So v prime equals 4 pi r squared times r prime, so there is our relationship. The volume's rate of change is equal to 4 pi r squared times r prime. So, and since there's an r in there, it means it will depend on r as we look forward. So from there, it says our next bet is to plug in the given information. Well, drawing some info out of the problem here, we know that air is being blown in at a constant rate of 10 centimeters cubed per second. That's a really important starting spot. So if air is being blown in at 10 centimeters cubed per second, that centimeters cubed gives me a hint as to what's being described here. Centimeters cubed is a way to measure a volume. So if we have 10 centimeters cubed per second, that's telling us v prime. So v prime in our situation is going to be 10, or 10 centimeters cubed per second. On the other side, we have 4 pi r squared, and r in our situation is that snapshot moment, 3. Now that we've differentiated, we can go ahead and plug it in. That means our equation amounts to 10 equals 4 pi 3 squared r prime. That's the same thing as 10 equals 9 times 4 is 36 pi r prime. And if we divide both sides by 36 pi, we'll get that r prime is equal to 5/18 pi. So we've got our answer. Of course, we could use a graphing calculator to confirm that. We should do that in just a second, but for the moment it's there. So with that as our answer, our final move is to determine what the units are. In this case, we're trying to talk about the rate of change of the radius, and radii are measured in centimeters here, and time is measured relative to seconds. So with that in mind, my guess would be that r prime is equal to 5/18 pi centimeters per second. And that should be my answer. If you didn't trust that again, if you wanted to make sure, you could do this in terms of units, centimeters cubed per second, and it's equal to, what do we have, 36 pi, and with r squared, that means that's 30, or here, let's do this way, just to clarify it. 4 pi times 3 centimeters squared times r prime. So we have centimeters squared over here, and we have centimeters cubed per second. If you imagine multiplying both sides by 1 / centimeters squared, you would get the exact answer we had, which was centimeters per second. So with that in place, we've actually answered our second related rates question. We were able to dig our way through and find what that answer was. Now, I did point out really quickly that since these are oftentimes calculator questions, since you're trying to do a realistic application, I want to point out that you got to be really careful here. And since this summer has brought up lots of confusion about the order of operations, I figure it's important to clarify how to put this into the calculator once. And then, of course, we'll kind of assume you can do it from now on. So, ignoring all the work that I did on the last lesson, we're interested in calculating 5/18 pi. So here's the thing. We know for sure that 5/18 pi can be done with the fraction button. We end up with 5/18 pi. And it tells us that's 0.0884. So there is our approximate answer. Now the problem is, if you put into the calculator 5 divided by 18 pi, using no parentheses, you get a very different answer. You get 0.873. And I can't tell you how many people accidentally write 0.873. The reason that 5 divided by 18 pi doesn't work is because of the order of operations. 5 divided by 18 times pi reads, according to order of operations, from left to right, because division and multiplication have the like operational magnitude, I'd call them. So in a sense, this would be reading in the calculator as 5 over 18. And then it would multiply times pi. So in a sense, that's not going to get us the correct answer. Our correct answer is 0.088. So I want to make sure that that's in there. And again, centimeters per second. But I want to make sure it's in there just because I've seen so many people reading this equation this summer. Wait, did I do that right? It's divided by 2. I have seen this asked. I've gotten text about this. I've gotten mentions on Snapchat about this. Seriously, like this is just the order of operations. It's just a really clunky thing. The intent might be to do something like 8 divided by 2 times 4, but this reads like so. So consider this your opening. So again, these are now multiplying. So this now becomes 4 times 4, which is 16. So consider your questions answered there too. But again, it can burn you, so be on the lookout. Okay, the second one in here. Very similar problem. In this case, I've just made one little change here. It says in this third example, while preparing for a party celebrating the end of homecoming, Courtney also helped inflate balloons. Just seems to be the thing to do at this point. The radius of her balloon increased according to the function r prime of t equals the natural log of t plus the square root of t plus 2. Now, I don't know about you, but I would love to see the sensor that brings out that information. The question then is, at what rate was Courtney breathing air into the balloon when r equals 3 centimeters at t equals 4? So the interesting thing about this problem, other than the fact that it's the similar equation, is that a lot of our work here is exactly the same. So specifically, we're going to follow the same basic process, and we've got the same basic picture. So even though I don't think either one's going to be thrilled with the depiction, let's just go ahead and pull this picture in again. And again, we've just got some different elements in here. So we're trying to attack this problem. I see once again we're talking about a spherical balloon. So I know that the volume, as given, is once again 4/3 pi r cubed. And now, nothing else here has really changed so far. In fact, if we go to differentiate with respect to time, we're going to get the same exact relationship we had before. Same shape, same, everything in that regard. So in this case, we're going to get v prime equals 4 pi r squared times r prime. So given that relationship, now our question is, what new information do we have to plug in? Because clearly something's different about this. We're told information about how fast the radius is changing, we're given time, and we've got this really complicated relationship for r prime of t. So in here, as we look, the first pieces of information I see given are r equals 3 and t equals 4. The r equals 3 part probably comes the fastest. That's just going to give us 4 pi 3 squared. The other part, the t equals 4 part, is probably going to be the hardest. But we can actually bring that into the problem by looking at r prime. R prime and r prime of t are exactly the same things. So what I can do is I can imagine multiplying by the full r prime of t. That is, we'd be multiplying by ln of t plus the square root of t plus 2. Now our problem here is, of course, that t is right now a variable that we've suddenly plugged into the equation. But remember, we were told that t equals 4. So we simply need to plug in 4 to this equation and we can get our relationship. So this becomes v prime equal to 36 pi. Then we'll have it multiplied times the ln of 4 plus the square root of 4 plus 2. And this is going to give us our rate of change for the volume. So basically all we had to do is we had to read out and interpret r prime of t as being the rate of change of r with respect to time, which I think makes sense with that notation, but it feels a little bit weird the first time you do it. Now, of course, this is our correct answer, but we'd probably want to enlist the help of a calculator to make sure that we do it correctly. So covering up the abomination I've drawn on the side of the screen, this would give us an answer of 36 pi times, it looks like the natural log of 4 plus the square root of 6. That tells us our answer is 210.814. So our rate of change of the volume with respect to time is 210.814. So it's growing pretty big, at least assuming not taking into account the scale. As far as units, we're talking about a rate of change of volume. So that would be centimeters cubed per time units. And time was given once again. Oh, interesting. This problem does not actually say what the time was measured in. I'm going to assume, for the sake of continuity, that we're talking about seconds once again. So I'm going to assume this is centimeters cubed per second, but that is actually a mistake on my part that hopefully will be corrected by the time you get the assignment. And of course, I forgot to change the color here, so let me make a quick little change so it looks like I didn't. Cover my tracks. And there is our answer. So I think this is a good time to just pause for a second and just let you kind of process things, maybe ask some questions or talk about and discuss what you've seen so far. So if you need to, feel free to pause. Otherwise, I'm going to move forward to the next example. Okay, now that we've seen some 3D geometry sort of situations, basically scenarios where you're given some relationship, a simple geometric relationship, and asked to move forward, I want to move on to a different type of problem that involves geometry once again, but that involves a different branch. So we're going to start by taking a look at the next example. This example features a yardstick, and it says that yardstick is leaned against a wall and has started sliding down. When the base is 24 inches from the wall, the base is moving at 10 inches per second. The question is, how fast is the top of the yardstick sliding down the wall? So normally in class, when I'm physically there and honestly able to stand up, which I can't really do right now, I would typically demonstrate this by having someone stand up and actually put a yardstick against a wall and watch it slide down to illustrate it. I've had to find some way to kind of work around that problem. So what I've created is this quick little demonstration. So this isn't perfect, but at least you'll get to see a little bit of what's happening here to kind of picture it. So notice what's happening, aside from the fact that the yardsticks seem to be multiplying, is it starts leaned nicely against the wall, and then slowly as it falls, notice that two things happen. First and foremost, can I draw on this? I can. So first and foremost, as it begins, we're given just a nice... Let's see if I can fix this really fast. Let's see if I can make one little move here. Let's do on click. See if that does the trick. So to start things off here, to kind of illustrate what we're looking at, we have a right triangle with the ruler as its hypotenuse. Now what happens is, as the thing begins to fall down, what changes is suddenly we get a different sized triangle. In fact, I discard. So let me go do some work here really fast, see if this will help a little bit. Let's put a couple of these on the click so that way we can see what's happening here with the triangle. So we start there. We have our triangle right here. And as we said, it's a right angle because we're assuming that the wall and the floor come together at a right angle. So after that, a couple more go down. So notice that now what's happened is we have the same hypotenuse, but suddenly our right triangle is wider and shorter. If we go a little further out, you can see that we end up with, once again, the same hypotenuse, because of course the ruler hasn't changed, or excuse me, the yardstick hasn't changed, but what's changed is the dimension of the triangles. So in this case, what we're seeing happen is we're modeling some sort of scenario that has a right triangle every single time, but as that right triangle moves along, what happens is, let's go back to our picture. I'll make my picture large enough. What happens is, as it moves along the wall, we have the height of that triangle decreasing and the width of that triangle increasing. So one is getting bigger and one is getting smaller. So our job here is to try to relate all this together and then work our way through and figure out at what rate the top is sliding down, knowing only what we know about how fast it's moving horizontally. So in here, as we go to get to work here, it says to start with a diagram, and I'm going to take advantage of the presence of that ruler or that yardstick that we already have. So basically the yardstick forms the hypotenuse of a right triangle. So there is the scenario that we're looking at. Of course that didn't work. There is our right triangle that we're looking at. And now as we picture this for the first time, I'm going to call the height y, and that's changing, so I do need a... I don't want to label it yet. Jeez, it's annoying to me. You know what? We're going to go out of order. I'd rather label it this case and think about that second. So your call. So from here, basically, I'm going to call this y, and we know that the height is decreasing because the yardstick is getting closer and closer to the floor. So it's changing, so I want to give it a variable name. And I also know that the horizontal distance is changing, and I'm going to call that x. That way we maintain the vertical y, horizontal x conventions that we've used so many times before. In addition then, that creates a third side, which is our hypotenuse. The difference is our hypotenuse, by virtue of being this ruler, or this yardstick, is not actually changing. So I don't need a variable name for it. I'm just going to label it as being 24 inches, because we know that it's 24 inches at all times. The ruler doesn't suddenly start shrinking or growing as it falls down the wall. Otherwise, that would affect things. So in this case, given that information, we now want to write our equation, having labeled this with as much information as we knew. So in writing our equation, we want to relate the side lengths of the right triangle to the hypotenuse, or the length of the yardstick. Well, we know a relationship that relates sides of a right triangle together. We know a squared plus b squared equals c squared. The difference is with our equation here, we have different variables, including one that's a constant. So instead of writing a squared plus b squared equals c squared, I'm going to write this as x squared plus y squared equals 24 squared. So looking at it from the outside, you might even point out that this looks like a circles equation. You're not wrong. For the moment, we have everything in place nicely. So there's our equation, and we've already pre-labeled our picture with those variables to make clear what's happening. So at this point, we're ready to differentiate with respect to t. And again, we're hoping everything cleans itself up nicely from here. So differentiating with respect to t, we're going to get 2x times x prime plus 2y times y prime. And again, that takes into account the fact that the horizontal distance is changing, it's getting bigger, and the vertical distance is getting smaller, so it's changing as well. And then the derivative of 24 squared, that's just a constant. In fact, I think it's 576, but whatever it is, its derivative with respect to any variable is 0. So there is the relationship we were looking for. So given this information, we've got to now... Oh, shoot, I've labeled something wrong, haven't I? Geez, why didn't you tell me? You should have warned me here. This length isn't actually 24, is it? It's a yardstick. A yardstick is 36 inches. I misread my own problem. My bad. So from here, though, if we know that's 36, we know that the base is 24 inches from the wall. We also know that at the snapshot moment, that moment when we want to pause and see what the rate is changing at, their length, our horizontal length, is going to be 24 inches. So given that, in a sense, we've got some values to plug in here. Like not the 24 part, obviously we said that had to be 36. That was my mistake. But down here, we now know that x is 24, and we know that the horizontal distance is moving out at 10 inches per second, meaning it's getting bigger. So that length is going to be a positive 10 inches per second. In fact, I'm even going to put the plus in there just for clarity's sake. So getting bigger implies positive. So in fact, I should say bigger implies positive rate. Now with that said, the next part is we're supposed to plug in y values. And we want to figure out the rate for y prime. So we know it's going to be 2 times something times y prime equal to 0. But the question is, how in the heck do we figure out what y itself is? We don't have that information. And the answer is it's not that bad. Basically, we have the Pythagorean theorem for us to work with. We just have two sides of that right triangle, so to find the third one, we just need the Pythagorean theorem itself. So basically, 24 squared plus y squared is going to be equal to 36 squared. Moving this around, we're going to get that y squared is equal to 36 squared minus 24 squared. And now, I guess I can pull out my calculator at this point. So 36 squared minus 24 squared, that's equal to 720. So basically we have y squared equals 720. And 720, by the way, is, let's see, 12 times 60, which is the same thing as 12 times 12 times 5. So 144 times 5. That means our y value is equal to the square root of 144 times 5, which is 12 root 5. So given that information, we now know y's value is 12 root 5. And that means we can plug it in here and get an equation that's available for us to solve. So simplifying what we have 20 times 24 plus 24 root 5 y prime is equal to 0. So now that we know that this is 24 root 5 plugged in, we've got everything ready to go. I'm going to leave the 24 there, but making some quick solution moves, or some moves here, we'll have 24 root 5 equals negative 20 times 24. At this point, I'm going to divide both sides by 24 root 5. And of course, you'll see why I left the 24 in there now. The 24's divide away. we're left with y prime equal to negative 20 over root 5. And if we rationalize, just because I have a feeling this is going to clean things up a little bit here, we're going to get negative 20 root 5 over 5, which is negative 4 root 5. So in our case, dy dt is equal to negative 4 root 5, which again we could find as a decimal if desired. But finally, our last move is to determine the units. Now in this case, I don't think we even need to go through and check all the pieces. I think we can just think this through. We're talking about how fast the vertical height is changing. The vertical height should be measured in the same inches. We kept things in inches, and then we were measuring per second. So this should be negative 4 root 5 inches per second. So that tells us how fast the top of that yardstick is falling down the wall at this moment. So you can kind of see there's some extra little stuff in here. If I were to go through and like point out all the extra little ingredients that were here, first and foremost, there was some conversion in here. It's not a favorite move of mine, but it's nice to kind of remind you that that might be a situation. Second, we had some things decreasing and some things increasing, so sign actually mattered. Like it was very important for me to have that negative sign over there and to make sure that we wrote that 10 as positive as well. So considering relative size was important. We had to use the Pythagorean theorem to work our way through and figure out the missing side, so we were given just enough information to work our way through. And then finally, we got to our answer, but that part wasn't that different. It was nice, though, to point out that our answer should have been negative because the height was decreasing or getting smaller, and we got a negative answer, which means we did well there. So this kind of exposes you to the world of kind of Pythagorean theorem style related rates problems, and we'll see a couple other contexts in just a second as well. Alrighty, the next problem that we would attack typically would be the following one involving the Mission Impossible 5 situation. So obviously I wrote this a little while ago. My plans to rewrite the entire lesson kind of got crapped up with my back. So in this problem, this first one, I would usually include this as a try it. We'd do some quick demonstration of what's there, and then I would have you go through. In our case here, I don't want to spend as much time working through it, so because of the fact that it's so similar to the previous one. So instead, I just want to demonstrate what's happening, and then we're going to skip part A and jump right to part B. I think that's a better use of time, particularly because I'm working really slowly today. I apologize. So in this situation, it says, while filming Mission Impossible 5, Tom Cruise's stunt double stands on top of a vertical elevator on the outside of a skyscraper. Standing 3,000 horizontal feet from the elevator's landing spot, Paula Patton watches the elevator descend down the building at 10 feet per second. And the question we're asked in this first part is how fast is the distance between Paula and the stuntman changing when he is 4,000 feet high? Now I've got a nice demonstration here, and of course if you look up in the upper right hand corner, you'll notice that Tom Cruise's stunt double is Tom Cruise, because he's basically does all sorts of his own stunts to his own body's harm. So whatever you think, at the very least you can appreciate the stunt skill that's out there. Now setting that part aside, our scenario has him moving down, or an elevator on which he is standing, moving down the side of a building. And so we can see it descending. Now of course the triangle isn't descending with him, but the idea would be as he descends, that angle on the bottom left corner slowly gets smaller and smaller, and the hypotenuse itself, he's going down into the ground. The hypotenuse itself would get a little bit smaller each time. But because Paula Patton's not moving from side to side, we don't have to account for that change that might be happening horizontally, although some cases you will. So with that said, part A would just involve us using a similar relationship to what we did before. The only difference would be that this horizontal distance would be constant. So we wouldn't want to go in there too deep. We don't want to spend too much time. Instead, I want to focus on part B of this question. So I'll paste in the work for this in a little bit. For now, I want to look at part B. Part B asks us, at what rate is the angle of elevation changing? Let's see. Let's make sure I do this correctly. There we go. At what rate is the angle of elevation changing as Paula watches the elevator in the above situation? So pulling some information here first, or pulling our little plan there, I want to focus on that question. So we're going to look one more time at the demonstration here, and I want you to tell me, as the elevator goes down, is the angle of elevation down here, labeled theta, is that angle increasing or decreasing? So imagine as it's happening, the triangle, we said it earlier I think in fact, the angle's getting smaller and smaller. So we're trying to find at what rate does that angle actually decrease over the course of that elevator's ride downward and apparently into the center of the earth with the way I animated it. So taking that in mind, I want to attack this problem because I think this one will work out much better. And although there are ways that could use the information we found in the previous problem, for now we're not going to focus on that. We're going to just focus on as simple as possible. So in this case, the first thing I want to do is I want to draw my situation a little bit here. Again, I have the advantage of a picture to work with in the first place. So there is the right triangle we're looking at, and there's the angle theta, the angle of elevation we were interested in the first place, from Paula to the elevator in the situation. Now again, we're going to assume for the second that Paula's not standing, that she's like lying flat on the ground, so that way her eyes are on ground level. We're just not going to worry about that height difference, although again, you should always be prepared to do that. But for the moment, we'll start with that information. Now, in looking at the information we have here, clearly y, the height of the elevator, is changing because the elevator is descending and moving down towards the ground. Likewise, the hypotenuse itself is changing, so I'm going to call that h for the moment. But at the same time, because Paula is 3,000 horizontal feet from the elevator's landing spot, and I realize I'm again labeling before anything else, I'm sorry. So 3,000 horizontal feet, that's not changing. She's parked down wherever it is that she's at, so that length is a constant. Other than that, the previous situation mentioned that the distance, that the elevator was 4,000 feet high. I'm also going to go ahead and label the 4,000 feet here, just to make sure that we have that in place. So that way we know it's 4,000 feet at the snapshot moment we're interested in. Now, with all that said, it says we're supposed to write an equation. But there are a few issues here. When we go to write the equation, we know that y is decreasing, and in fact we know the rate that the elevator is descending, so we know that this is descending at 10 feet per second, and specifically it's really negative 10 feet per second, and we know this isn't changing at all, so this is constant. What we don't know at this moment is we don't know the rate at which h is changing. Like, h prime is clearly changing, and if we'd done part A, as originally designed, you would know what h prime was changing at, but at the moment we don't know. But I aim to prove to you that we actually don't need to know. And the reason is, what we want to relate things together that somehow involve the angle. So my thought is, if we want to talk about an angle's rate of change, we should simply go forward and use a trig relationship. So since we're missing some information about h, I want to write a relationship that involves this side and this side, the sides that we know all the information for, that we were given the info towards. And if we look at this triangle then, relative to angle theta, we have the opposite side and the adjacent side. So if you're hearing opposite and adjacent, I'm hoping that your mind naturally, in addition to thinking of SOHCAHTOA, immediately jumps to tangent. So what if we took as our equation, tangent of theta equals the opposite, which is y, and it's changing, so we'll use a variable, over the adjacent, which is 3,000, which is not changing, so we can keep it as a constant. So this relationship involves theta, and it involves the things that are changing. So I think we have our relationship. So at this point, that's our first move, is just being able to set up the equation. Now, as a quick little aside, if you chose to go with cotangent and did 3,000 over y, you would, assuming we all did the correct work, you would get the correct answer. Same thing if you figured out what h prime was and you used sine of theta or cosecant of theta, you would get the correct answer as well. It might just take a little bit longer and involve some extra differentiation. At this point, though, this would be what I'd call the easiest possible relationship. Not only because it uses the information provided in the problem, which is a nice secure thing, but also because the derivative on the right side is going to be really easy. That's actually linear, so taking the derivative should be fast. So as far as differentiating, on the left side we have tangent of theta. So don't forget that theta is a variable. That means when we take the derivative, first we do the derivative of tangent, which is secant squared. Then we multiply by the derivative of theta, which is our derivative of the inside. So on the left, we get secant squared of theta times theta prime. On the right, since that is really the same thing as 1 over 3,000 times y, being linear, we can actually jump through that really fast. And we can take advantage of the fact that the derivative is just 1 over 3,000 times y prime. Clean, right? Works out really nicely. Now, given this information, we have our differentiation done. Now it's a matter of plugging in the right information. So in looking up here, we know the specific y value is 4,000, but it doesn't even bring up y in this case. That's unfortunate. In addition, we've got, so stuff that we do know here. This is y prime. So in my equation, I can write this as 1 over 3,000 times negative 10. Because y prime was the rate at which the elevator was descending, there it is. On the other side, for secant of theta, we don't know what secant of theta is right now, but the one thing that we can do is we can at least get it over to the other side, so we can play with it in a second. So what I'm going to do is I'm going to multiply both sides of this equation, before we even worry about the value of it, by the reciprocal 1 over secant squared. That way we can at least clear it over and get theta prime by itself, since that's our ultimate goal. Now when we do that, we do get theta prime, or d theta dt, and in a sense this ends up getting us negative 1 over 300. For the 1 over secant squared though, I'm hoping that you'll trust me when I say that that's the same thing as cosine squared, or cosine of theta squared. That way we have all that information present. The reason that this switch was so helpful is now our question kind of comes down to, can we figure out what cosine of theta is in this instant? Like at this moment we snapshotted the scenario, do we know what cosine of theta is? Well, we know cosine of theta is equal to the adjacent over the hypotenuse. And we do know that adjacent is 3000. Like that answer, that value is literally adjacent to our work. The problem is we don't know what the hypotenuse is. And so at first that can kind of throw people, but we can find the hypotenuse using the Pythagorean theorem if necessary. Specifically, 3000 squared plus 4000 squared has to equal h squared. Now this is actually a 3-4-5 right triangle here. It's similar to or proportional to a 3-4-5. So I'm going to go ahead and point out that the hypotenuse is 5000. But if you wanted to solve that, you obviously could. And the nice thing is that tells us that cosine is actually just 3 over 5. So moving back into our expression, we'll have that d theta dt, or theta prime, is negative 1 over 300 times 3/5, the cosine value at this moment we were interested in, squared. Simplifying all these ingredients, we'll have negative 1 times 3, you'll see why I do this in just a second, over 300 times 25. Now one of those 3's can divide away and clean up with this 100. And as far as everything else, we're going to get that our value is negative 3 over 2500. So there is the numeric value. That's the rate at which the angle of elevation is changing. So in other words, this tells us that the angle of elevation is decreasing, which we expected in the first place. As far as units go, I can admit that this is a little bit tough. I think you're probably safe in understanding that this will be per second, simply because of the fact that we're dealing with seconds. But I think that the other part can be a little bit tougher. We're measuring how fast an angle changes, and since we're using these nice derivative rules, that means we have to use radians. So in other words, what we're talking about in our angle isn't in degrees, we're talking about the radians per second. So in our case, we're going to get that the angular rate of change is in negative 3 over 2500 radians per second. And there is our answer. So now it is possible to get this in degrees per second, but if you were to do that, you would need to actually do the conversion and multiply by, like convert radians to degrees. So possible, but just not necessarily what I want to deal with right now. So again, lots of stuff in here, especially important because this is one of those like every year problems that comes up. Although I will remind you that the video solutions have multiple examples. I did almost every problem on the problem set for tonight, or for this week. And in looking in here, the big things to note though were that we had to choose a trig relationship to relate our angle to the information we had in the problem. Any trig ratio would have worked, but we chose the one that we had the information provided for. That way too we're covered in case we'd made a mistake calculating this in part A. Once we did that, we differentiated, and probably the weirdest thing to come up in here was that we ended up with a cosine of theta in our problem. But remember, we were looking to plug in the value at that snapshot moment, and the cosine of theta at that moment is 3000 over what we found to be 5000. So after that, it was just a matter of plugging and chugging our way through the rest of the problem. So I realize, again, this can be kind of challenging, but there's lots of video solutions. I did all the problems that had this technique in the video solutions. So if you need to see more there, you can. Otherwise, you can also, of course, pause the video, talk about it a little bit, ask some questions, and see if you can get somewhere. So there was the Pythagorean theorem angular elevation problem, another common type or trope within this unit. With all that said, this brings us to our final two examples. I'm sorry this takes a little bit longer. Again, I can't really maintain the pace that I want, and having a really bad pain day today. Lovely August 5th, 1 week before I have to report to school. But this does bring us to that final section, so let's get right in there and take a look at the last types of problems that you kind of run into commonly. And again, the video solutions should help you as you're working your way through these for the first time. So in our second to last example here, our situation begins by making reference to the fact that the hot power forward on the Kings seems to change every year as we draft more people. So this one says the Kings 7-foot-tall power forward Marvin Bagley III, that's a pretty good future I'd say, is walking toward a 21-foot-tall street lamp such that his shadow is shrinking by 3 feet per second. At what rate is Marvin Bagley III walking? So in this case, ignore the fact that that's a picture of Demarcus Cousins down there. I couldn't find the original file to make this change. I want to make sure I finished it. But basically, this is kind of a weird scenario to look at. And I believe that I actually have a demonstration on the computer that shows this a little bit. So let me go see if I can find that and help us take a look at it here. Give me 1 second. Okay, 1000. Welcome back here. So here is what I had come up with last year. I made it for a different problem where there was a beanstalk and a street lamp on top of a beanstalk and all that stuff, but I cleaned it up so that it fit our scenario a little bit better. So it's a little awkward the first time you see this, so I'm just going to try to illustrate what's happening here. So we've got a street lamp, as the picture shows right here, we've got a street lamp shining light down. Of course it shines in all directions, but you can imagine dropping a vertical or perpendicular right there. And then because of the presence of our power forward, Marvin Bagley III, that light casts a shadow right here. So our shadow would be right there on the ground. And as Marvin moves either toward or away from the street lamp's source, he creates a different size shadow. So here's a nice little illustration of what it looks like. Oh gee, it's going really fast. Hold on. Whoa there, fella. Doesn't I not get to slow it down at all? Do I not get to slow this down at all? Okay, well I guess I'm going to have to drag it. So as Bagley walks away from the street lamp, look at his shadow. That shadow is getting longer. It's getting longer and longer, of course. And each time it does, though, of course, it doesn't change the structure of the problem. Structurally here, we can see what we have, our right triangles. And in particular, I'd say that these are what we'd say are proportional or similar right triangles. The large triangle, formed between the street lamp, the edge of his shadow, and the base, is proportional to the one formed by Bagley and his shadow in that area. So basically what we want to do is we want to go through and we want to figure out the rates at which this walking by Bagley changes the rates at which the shadow is growing. Because obviously he's moving really slowly, the shadow is growing, but it's not growing that fast, but he moves faster than the shadow grows. We don't know if those are proportional or not, or what that relationship is at least. So that's our scenario. What we have are proportional similar right triangles, and we're going to work from there. So in digging in, I have the advantage of already having a picture here, so I'm going to take full advantage. And now I'm going to work you through and talk about the structure here and how we can label this for success. So in our diagram, which we already have, I mentioned the presence of triangles. So, you know what, actually, what the heck, we see that picture. Let's just draw the triangle right off to the side. Aside from the fact that I have trouble drawing lines. Okay, so there's our triangle. There's our second triangle. So I mentioned already that these were both right triangles. In addition, as far as things that aren't changing here, the street lamp is going to say, and again, I'm labeling my diagram. Jeez, I'm sorry. I just can't stop myself from doing that second sometimes. So the street lamp is 21 feet tall. And although Bagley's young enough that he might still be growing a little bit, I think incrementally, moment to moment, it's probably not going to be a big change. So we know that Bagley himself is also 7 feet tall. Things that we know that are changing, though, we know that the length of his shadow is changing, L. Closer to the thing, further away. The shadow gets bigger as he walks further away. So we know that's changing. And then finally, this is the thing that usually gets people. His distance from the base of the street lamp is changing as well. And I'm going to call that D, his distance from the street lamp. So in this case, I'm going to label this and actually write out what they are. That's probably a good habit in general. But this is his shadow length. Shadow, shadow, shadow. There's his shadow length. Hopefully the shadow doesn't come to life. That would be spooky. And then D is going to be his distance from the lamp. I actually have to say street lamp, because when I say lamp, I think of genies. When I think of genies, I think of Aladdin and all sorts of other stuff. So I think of a whole new world. So there we go. So we got both those two pieces on there. Those are the things that are changing. Now, of course, there are other elements that are changing. These hypotenuse lengths are changing too, but they're not relevant to the change that we're interested in, which is all relevant to the rate at which Marvin Bagley's walking and the rate at which his shadow is changing. So in here, let's look at our situation. So interestingly enough, as we start to determine an equation here, a couple things that I notice is first that it says that he's walking toward a 21-foot tall street lamp. So although that's not necessarily going to help us with our equation, it's important to note that I was actually slightly wrong in what I was doing. In a sense, he's walking towards it, so his shadow is getting smaller. So that's going to be relevant for us to consider as we get closer and closer to the scenario. We want to account for that shrinkage of his shadow. So in here, as far as equation pieces, I want to relate the stuff that's together, and what I'm going to do is I'm going to create a statement of proportionality. Now, a lot of people get confused when I do this statement of proportionality for the first time, but basically you could imagine if we called this angle theta, we would have the same angle theta for the big triangle as for the little triangle, and so we could set up each one as being a tangent. More or less though, instead, if you don't like that, well, yeah, if you don't like that, that's okay. What we could set up instead is like pieces. So for instance, using the small triangle first, this first part, the small triangle, I could do a ratio of the length of the shadow to the height of the Bagley. That ratio has to be equivalent to the proportional ratio between the full triangle. And the full triangle, if we're going here, has L plus D as its base and 21 as its height. So right there we get our equation. This comes out, or comes from the similarity statement, I guess would be a good way to say it. Good to say. This is the statement of proportionality. I think that's a good way to say it too, although again my mind's not fully here. So we've got those ingredients both in place. So we've got our equation set up. Our diagram's already labeled, which means it's up for us to differentiate this implicitly. When we go to differentiate it implicitly though, there's a couple things that I see here. First and foremost, I see that we've got kind of these awkward fractions. So to simplify things, I'm actually going to pause it for just a second before I differentiate, and I'm going to rewrite this equation in a slightly cleaner form. I'm in fact going to cross multiply. You'll see why in just a second. So in this case we have 21L would be equal to 7 quantity L plus D, and that means we get 21L equals 7L plus 7D. So that is the exact same equation. It's just been cleaned up quite a bit. And in fact, we can clean it up a little bit more. By subtracting 7L from both sides, we can actually get that 14L is equal to 7D. Not 7D. 7 times the quantity D for distance. So with those two things in place, now we've got a really simple equation to differentiate. So we're ready to take the derivative with respect to t. So when we do that, went too high with my little swoop. When we do that, we'll get 14L prime equals 7D prime. And now you're looking at this equation. We could, of course, divide by 7 on both sides, but I'm going to pause for just a second and look at what information we have to plug in here. Because what's interesting in this case is you'll notice that it doesn't depend on the actual distance or length of the shadow L or the distance D. These are always proportional in this way. It's always proportional, so we don't need to go that far. Instead, we just need to plug in the rates. And what it says in our problem is that the shadow is shrinking by 3 feet per second. What that tells me is that L prime is equal to negative 3 feet per second. The negative to ensure that our length is getting smaller. So plugging that information into our equation, we'll get 14 times negative 3 equals 7D prime. That's going to be negative 42, 7D prime. And if we divide both sides by 7, we're going to get that negative 6 is equal to D prime. So that tells us that the distance itself is decreasing by 6 units of motion. So in other words, it's getting smaller, which we should expect, of course. We saw that in our diagram here, or in our picture, that as he gets closer, that distance between them is getting smaller as well. More than that, though, we just need our units to finish off this problem, having seen everything else in here. So to wrap this up, d prime, or dd dt, which is kind of fun to say actually, dd dt, dd com. So d prime is going to be equal to negative 6, or decreasing by 6, and then as far as units, it's a distance over time, which means we're going to use the same units. So this will be negative 6 feet per second. So with that said, there's everything in place. We were using proportionality, we were using similarity statements. Again, if you're interested in more how that similarity statement comes in, I mentioned the fact that we could set them both equal to tangent of theta. But in any event, the important steps here were the same process, but we set up a statement of proportionality. We cleaned it up a little bit to make sure that it was easy to differentiate, and then we plugged in the information. And as it turned out, it didn't even depend on how far away each of those people were at any moment. So there is the first of 2 similarity-based kinds of scenarios. Our second similarity-based scenario and final problem that we're going to hit is another like staple of this unit and of this topic, which is another technique to test out. And this one involves a right circular cone. And in this case, what's going to be happening is water is either going to be poured into or dripped out of a right circular cone. And we're going to be interested in determining some information about how that change affects the liquid inside the shape. So in our problem itself, we are told that Mr. Burns and Smithers locate a right circular cone-shaped tank, because, yeah, it's a totally natural thing. It has depth 20 feet. So, I'm going to go ahead and label this thing as my diagram since I'm here. So we say that the depth is 20 feet. And it says it has a radius of 10 feet. So the total radius up there is going to be 10 feet as well. And again, since it's a tank, we know those two things aren't changing right now. They're just the dimensions of the tank itself. Using a crane, they then lift it up and drain it over Lake Springfield. Watching nearby, Lisa notes that the surface height of the waste is falling at a rate of 0.5 feet per hour. At what rate is nuclear waste leaving the tank when the water is 8 feet deep? So with all that stuff present, we have to kind of picture what's happening here. So there's already, when we start, some liquid inside this tank. And in fact, if we picture what that liquid would look like, it would look like it's sitting kind of inside this stuff. So all of this is liquid waste. And I'm making it kind of a radioactive green because if you ever watched The Simpsons, Springfield has a nuclear power plant. So with this in place, their idea here is that as this liquid drains out into the lake, I realized if I could rotate Monty Burns, I could literally rotate his head and he'd be drinking the radiation, but maybe that's cruel. So, oh, come on, really? Whatever. So as this goes through, hopefully what you're going to notice really quickly here is that as liquid drains out, the shape itself stays proportional. We just basically get a mini cone full of radioactive waste. Yay! And our interest here is an interest in how fast the waste is leaving the tank. At a given moment. So what we're seeing and what we're told is that we know the rate at which the liquid is leaving. We know the rate at which the liquid is leaving at... Sorry, this is just annoying me. There we go. We know the rate at which the liquid is leaving, or we don't know the rate at which the liquid is leaving. We know the rate at which the height of liquid inside the cone is leaving. So basically what we are interested in is determining how fast the liquid's leaving down here, which I would probably want to call V prime, because that's like the amount of liquid waste that's leaving. And what we're given is how fast this height, h, is changing. And look at that, I already labeled the entire thing. So there's our scenario. We've got little mini cones that are working their way through. So as we go forward and we write our equation, we do need to know the volume of a cone. And this is honestly just my mistake for not including it here. The volume of a cone is pi over 3 r squared h. So that is the volume of a cone with radius r and height h. So given that that is our volume, which again it should be on your page already, we can go ahead and differentiate this. There's just one big problem that's kind of jumping out at me here. As we go to differentiate this, we have two different variables, which suggests to me right now that we're actually going to need the product rule. And again, if you hate the product rule for some reason, get over yourself, but I will show you a second way. But for the moment, let's just kind of play along. So the radius and height are both obviously changing. So when we go to differentiate this, we're going to get v prime equals pi over 3 times, and I'm just treat it as a scalar, it'll be 2r r prime times h plus r squared times h prime. So there's the product rule work. In looking at this, though, we have some issues. Now that we have this, if we go to plug in from here, now that we have the full derivative, plugging in is going to cause us some problems. We know that the height of water at this instant, h, is 8, so we know what we can plug in right there. But we don't know what r is equal to at this moment. So there's already some issues started right there. Second, we know the rate at which the height is changing. It says that the surface height is falling at 0.5 feet per second, but we don't know how fast the radius is changing. So unfortunately, although this isn't an impossible way to do the problem, you can kind of see that this is fairly difficult because there's a lot of information that we don't actually have here just yet. So what I'm going to do is I'm going to recommend that we not go through the full product rule method, because that's a fairly challenging move. Instead, what I'm going to recommend is we take advantage of the fact that these cones, the full-sized one and the cone of radioactive waste, are actually proportional to one another. So before we jump in and start using our full equation, we should take into account that R and H are always connected to one another. In fact, looking at our picture one more time, as H gets smaller, so too obviously does the radius, and they maintain that proportion the entire time. So where I'm going to begin is by writing a similarity statement. I want to connect the radius and height together and take into account the fact that they're always going to maintain the same proportion. So looking up here, if I look at the ratio of R to H in this cone, it's always going to maintain the same ratio as it did at the very beginning, when the cone had a radius of 10 feet and a height of 20 feet. So again, these give us the original proportion for our cone. Given that, that means that R over H is equal to 1/2. In other words, the radius is always half of the height. And if that's true, then we can literally write that as an explicit equation. Multiply this equation by H on both sides, and you're going to get that R is equal to half of the height. No matter where we're at, no matter how much liquid is in there, we're always going to maintain that aspect ratio, if you will. So what I'm going to do is I'm going to use this, and I'm going to make a substitution. Remember how we were trying to differentiate this relationship a second ago, and we ran into the issue with the product rule? That's awfully small. Let me make it bigger. What we're going to do instead is we're going to make a quick pause, and we're going to take that proportionality statement and that connection and plug it into the equation for the volume, so that way our volume equation will have no more R in it, it will only have H's. So in looking up here, rewriting this equation, we can write it as pi over 3 times R, which we are explaining and writing as 1/2 H to maintain that proportionality. So it's pi over 3 R squared times H. Simplifying this out, we get pi over 3 times 1/4 H squared times H, which cleans itself up to pi over 12 times H cubed. So what this gives us is our new simplified volume equation. Our equation is V equals pi over 12 times H cubed. In other words, we don't even need to include the radius anymore. That radius's change is proportional to the height, so why deal with two variables when we can focus on the one we know information about? With all that in place, now we're ready to finally differentiate, and we'll be able to take advantage of the exact information we're provided. So looking in here, our derivative is going to be v prime equals, of course, the scalar property pi over 12 times 3h squared. And then, of course, h is changing, so we multiply by h prime. There's that implicit chain rule kind of work popping in. Now, of course, this cleans itself up a little bit. V prime is equal to pi over 4 h squared h prime. But for us, the most important thing to hit here is to now plug in the information that we know and that we were given. Looking at our information, we know a couple different things here. We know that the height is changing at negative 0.5. We know that the height at this instant we're interested in, the snapshot moment, is 8 feet. And hey, look at that. Those are all the variables that we were actually missing. So given this information, we have that v prime is equal to, looks like pi over 4 h squared times our height, which was negative 0.5, same thing as negative 1/2. Given that information, we'll get that v prime is pi over 4 times 64 times 1/2 is negative 32, which means our volume's rate of change is negative 8 pi. And as far as units go, just to wrap this thing up, wrap this puppy up, we're going to have volume is feet cubed per hour. And there is the rate at which the volume is changing. So again, don't let me discourage you too much. Like, the product rule is great, and especially recognizing it is really good. But our goal here was to take advantage of the fact that we were given lots of information about the height and how fast it was changing. So instead, what we did was we set up a similarity statement, since the cone maintains that proportion of half as long as the height being twice as long as the radius being half the height. There's a better way to say it. And we drew that information into our equation, so that way we'd have everything about the volume in terms of h. Once we had that, we differentiated like normal. It was just like someone gave us an equation that was easy to work with. We took the derivative, we plugged in the known information, which again was all about h, and we were able to get our rate of change. And of course, this tells us that the volume was decreasing, which we should expect because the radioactive waste was pouring into the lake. So as I've said many times before, this might be one to go back to, listen to one more time, or to ask some questions and discuss a little bit, just because it's a little bit weird. But again, there's multiple on your problem set for the next couple days, and I have video solutions for a couple of them to make sure that you're comfortable with what that looks like as well. As again, it's another one of those like guaranteed to run into questions that's out there. So with that said, I believe that ends. Oh, there's Bagley. He was here all along. So, with that said, what we've worked through today has been the entirety of related rates. So giving you kind of a quick little overview and reminder, related rates takes our implicit differentiation technique and it moves it forward to take into account that any variable could be changing with respect to time. As soon as we have to differentiate with respect to time, suddenly every variable needs that x prime or y prime, and that opened up this new world. We looked at some really basic examples with just straight up connections between x and y, but more commonly we dealt with geometrically defined situations, where we were trying to figure out how fast change in one element changes something else. First one dealt with length of a side of square changing and how it impacted the area, but we had ones involving sphere volume and radius length. We had the Pythagorean scenarios where something was falling, or like the elements of a right triangle were changing over time. We skipped one, sorry. And then we did one involving the angular rate of change, talking about the fact that any ratio could work, but some trig ratios allow for a really easy differentiation or take advantage of the information you're provided in the problem. Finally, we moved on to similarity scenarios, starting first with the Sacramento Kings walking power forward scenario, where we dealt with shadow length and looked at how we could picture this scenario and even model it out nicely on Desmos. By the way, if I can find a link, I'll give you this so you can kind of play with it a little bit. And then finally we dealt with one more scenario, which was kind of the 3D geometry proportionality scenario, which in this case dealt with a cone. And cones are the ones where this actually works, because the radius and height are proportional to one another, so that when one changes, the other one does too, but at a similar proportional rate. So given all that information, obviously this isn't exhaustive, this just kind of runs through like the most common tropes and types of problems in the related rates world. But of course your problem set tonight will feature some more variety and some different type questions. And over the next few days, once you finish this, we'll start practicing in class with what I hope will be a Cuddles movie. Maybe one from before if I'm not able to work while I have back surgery, or it might be a completely brand new one if I can get everything together and do some sitting and working. So in any event, thank you for watching. I'll be honest with you, I am really disappointed with how these lectures have turned out, simply because of the fact that I haven't been able to make them as funny and enjoyable as I wanted to, because in the possibility of having surgery, I need to stay off of any pain medication, so I've just kind of been physically miserable a lot of the time, especially today. But I hope at the same time I've provided you some good instruction and that you're getting extra support, and that the video solutions that I've kind of spent the summer working on have been helpful tools as well. Obviously, I'd rather be there. I'd rather not be dealing with this, but I'm hoping this is a good investment so that we can have a great rest of the year. So thank you for all the attention and work you're putting in. Thanks for trying to make me proud as you work through all the curriculum and calculus, and you learn from every tool that you have available to you. And again, I'm sorry these haven't been as enjoyable as I'd like them to be, and I like to think class could have been if I was still there. But I have confidence in you, and I'm hopeful that these have been very valuable tools nonetheless, justifying the time that's been put in. So without further ado, this is the final one of these lectures according to the plan that I have and the schedule that I was given for surgery. So thank you for watching and learning, and as always, have a great day.